let's start. So what we were doing previously was, we were doing functions. We were doing graphs. Okay. Okay. Yes. We were doing functions, right? What were functions? They were basically a really unique way to define inputs and outputs. Or you could say it was how we
Cause and
connected
effect.
the cause and effect of anything, right? You could relate any cause and effect together, right? So for example, we did this really good example of grades are a function of your study time. Now, what is the cause? I'm sure the study time is your cause and the effect is the grade, right? That when you press your certain button of study time, right, this is the input that you put in, and what is that the output you get? What is the result that you get? That's your grades, right? So that's just a way of writing functions. Okay, any questions up till this point, by the way?
No.
No. Okay, so we were going along with this once again. Are we recording? Yes, we are. Okay, so what we were saying is that y is a function of x. When we say y is a function of x, we mean that x is our input, okay, and y is our output. And or you could call it the x is your cause and y is your effect, right? So what we do is we already write the cause on the x-axis, and we see the effect of that cause, which is the effect, right? That is what we write on the y-axis. Okay. So generally what we see is we've chosen our, cause or our input to be, screen time. And because of that screen time, let's say, some children get a certain number of dant per day, which is the effect. So that means if you have 1 hour of screen time, let's say you get one dant per day. If you have 3 hours of screen time, you get three. For example, if you have like, I don't know, 10 hours of screen time and you get like 9 dant per day. So that's basically simply a way to write cause and effect, that if you keep increasing the cause, in this case, the effect also keeps increasing, right? It's basically how we're studying relationships. Now, what we're going to do is we're going to have a slightly unique example. Okay, it's a very interesting example. So these are three lines, okay, for three different children. Okay, so this blue line is for a different kid, this green line is for a different kid, and the red line is for the different kid. Okay. Now, all three of these people, okay, they have a slightly different relationship between screen time and dart by their parents. Okay. Now, out of these lines, like just from these lines, can you figure out which one has the most strict parents by this graph? What do you think?
Is it the green one and the red one?
Hmm. Okay. In fact, the green one is sort of in the middle, but the red ones have the most strict parents. These ones are the most strict ones. These are average. Blue is pretty lenient. They don't even care about their kid. Okay. So now how do we like even, define that? If you look at the graph, have a look at 1 hour screen time, right? So this is the screen time hours, like one. Okay. And for every 1 hour of screen time, you see that the average kid will get one dart, right? Do you see that on the y-axis? This is y-axis is the dart, okay. And for the same 1 hour of screen time, do you see that the strict kid is getting like 3 dart per day? Can you look
Yeah.
at it on the graph, right? And what about the lenient kid? That kid is barely even getting half of dart. So that means he would actually have to get 2 hours of screen time to get 1 hour of, sorry, one dart per day, right? Makes sense? Do you see how we can read off the graph? For example, you can
Yeah.
also pick it off for 2 hours. So if you have 2 hours of screen time, you see that the lenient kid only gets one dart. If you have 2 hours of screen time, the average kid gets two darts, and the kid with 2 hours of screen time is going to get six darts, right? So that's like the strict parents are pretty harsh on the kid, and they are going to taunt them, and they're going to ground them much 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 more than the average or the lenient kid. Okay, then we'll study a slightly different relationship as well. What do you think this graph is telling me? So this is another graph This is for three different people. So this is for yellow, which is another kid. There's a green one, which is the average kid. And then there's this red anomaly as well. What do you think these three lines are telling me? These are like three separate cases.
The yellow one's telling me that the parents are out of their mind because they
Ah,
zero screen time, but two don't.
exactly. So you see that the yellow one, these people are crazy, right? They're just trying to, somehow put off their anger on their kid. Even if you have 0 hours of screen time, 0 hour of screen, what you're getting is you're already getting like 3 dant per day, which is absolutely horrible, right? That means, for example, if you have 1 hour of screen time, you see that you're getting 4 dant. Now you're already getting three no matter what you do. So you might as well, just use 1 hour and get four. That's how this kid operates. Then you got this average kid. This is the same one as before. 1 hour of screen time, 1 hour of data. 2 hours of screen time, 2 times data. A very linear relationship. What about this red one?
The red one is like the parents are pretty chill. Even if it's 10 hours, he's only getting one
Haha.
done.
Exactly. So that means that these parents, this kid is either adopted, okay, or you could say parents don't care. You can do whatever you want. We don't care about you. We're done with you, right? So you can classify all kinds of relationship by simply a graph, right? You see that for this kid, you have like 100 plus hours, and you still get 0 dot, right? Now all of these ways where we somehow plotted some kind of relationship between the x and y, they're all just trying to tell a story. The point of a graph is to tell me a story of how that case is between the relationship, between y and x. This is the cause and this is the effect, right? Now, where this was just an example. We're going to try to use these like the straight line, the horizontal line. There's some lines that that are shifted upwards. How do we use them, or how do we define them mathematically? We need to have a certain uh you could say a certain set of very very fixed rules, that how do we define a line.
Terminology?
uh, yes, exactly. Terminology. Like, for example, how do we differentiate this line from this line from this line, right? We need to be able to differentiate them. How do we like define these lines? How do we separate this line from this line? The word for that is gradient, and we're going to get to gradients in just a bit, or we call it slopes. And then there are some lines that are, shifted up and down. There's a word for that as well. You see that this line has been shifted upwards, or it's crossing at a certain point. It's cutting the y-axis at a certain point, and this is what we call the y-intercept. This is what we call the y-intercept. So we need to be able to play around with the graphs, and we need to know what to call what. So we're going to do that in just a bit. So any line, this, for example, this green line, this yellow line, this red line, any line has an equation associated with it. And that equation is always in the form, this is very, very important. It's always in the form y is equals to mx plus c. Have you ever seen this equation? Yes, Avia.
Yes,
Have you
many
seen
times.
this? Yes, many times. Does it haunt you in your sleep or no? Do you know what
No,
it
it's
means?
just, yeah, it's
What
like
is it?
it's like the
Hmm.
form, like the
Hmm.
C is the y-intercept and
Hmm.
mx is the gradient.
Exactly. So what we see is that this m is basically what we call the gradient. The gradient. This C is what we call the y-intercept. We'll see how to use this line in just a bit, because it's really important. And X is basically what? This is my input, right? I'm going to press a certain input X, and I'm going to get a certain output Y. This is my output, right? And this gradient will basically intensify the input. That means, for example, if I press the button 1 and my gradient is 2, that means that the effect of the input is going to be decided by the gradient. We'll do an example. For example, this is an equation. This is an example. Y is equals to 2x plus 1. Now, I can already, break this equation into parts. What happens is this 2 is the gradient. Why? Because it's being multiplied by x. This 1 is my y-intercept. Now, what is the y-intercept? That's basically the point at which you cut the y-axis, and then x is basically my input variable. That means I can keep on changing x however I want, and it will give a unique output y. Okay, so that means if y is equals to 2x plus 1, let's see. If I press the button 0, that means this is just going to be what? It's going to be y is equals to 2 times 0 plus 1, which is just equals to plus 1, right? And then if I press the button 1 for x, I'm just going to get 2 times 1 plus 1. That's just 3, right? If I press the button 2, I do what? 2 multiplied by 2, 4 plus 1,
5.
which is 5. And do you see that every time I press
Yeah,
a certain button, right?
increase by
This
2.
is my, exactly. This is the button that I press. Doesn't that mean that x is my cause? And what is the effect in this case?
Why?
Why? Right? Because if I don't press the button of x, I am not going to get a certain output y. So this y is equals to 2x plus 1 is basically, it's basically that y is dependent on x. Dependent on x. That's what a function is. This is what a function. This is a function. That means this is just a machine that when I press a certain X button, that machine is going to pop up a certain Y output. So that's what a function is. You can even try to plot it. So for example, that means if I press button X as 0, right? If I press the machine 0, I am going to get a button of Y, right? So at 0x, I'm going to get Y as 1. That means regardless of whether you have an input, you are always going to get 1, okay? Then when you press the button of x1, you get 3, right? That this line. Then when you press button of x2, you get what? You get 5. Then you get 7. Then you get 9. And this is the line that somehow forms just from your function. And this is what? This is basically a function. This is a function with what form? With the form y is equals to 2x plus 1. Make sense? That's basically what a function is. This is just describing the relationship between my cause, which is x, and y, which is my effect. Make sense? Perfect. So far, or no?
Yeah.
Yes? Okay. Now, now we're going to move on to the gradient. The gradient is one of the most useful skill in all of mathematics. It is so important. It is so important. It is so important that if you understand the gradient, you will be able to really understand what the numbers mean. You will be able to understand causes and effect. You will be able to understand how graphs work. You will be able to understand the relationship between any two variables. So the gradient, by the way, has multiple names. You can also call it slope. Okay. You can also call it steepness. You can also call the gradient as, there's another word, what was it? Gradient, slope, steepness, and I think that's about it. Gradient. Yeah, that's it. So the gradient, or we also call it as M. M. So M, what is M? The gradient can be written as rise over run. It can be written as change in y over change in x. It can also be written as y2 minus y1 over x2 minus x1. It can also be written as dy over dx. Okay. It can also be written as, for example, that's about it. I think I've written it all. So now what does the gradient really represent? The gradient basically tells you, the keyword is, with me so far, Nabia?
Yes.
Yes. I think you're bored without your sister. Or are you having the most fun time of your life?
The second option.
Okay, okay. She's going to get this recording, by the way. Okay.
Oops.
Okay. So the gradient is basically that by how much, very carefully listen, by how much does y increase, okay, when x increases by 1 unit? Or in terms of the cause and effect relationship, you could think of it like this, that when cause increases by 1 unit, okay, when cause increases by 1 unit, 1 unit, by how much does the effect increase? That's basically the interpretation of the gradient. By how much does the effect increase. So it's basically, it's kind of like saying that when I increase my effect a little bit, sorry, when I increase the cause a little bit, what effect does that have on my effect? That's basically what the gradient means. Now, for example, if my gradient is 2 in this case, right, I can see that y is equals to 2x plus 1. This m is equals to 2, right? Now, if m is equals to 2, what does that really mean? Now, since gradient is basically change in y, 1 second. So if the gradient is basically just change in y over change in x, and I got my answer as 2, okay? I like it, figured out already that the gradient is equals to 2. Now, what does that gradient m is equals to 2 mean? What do you think? Yes, Navia. What does m is equals to 2 mean?
That's like, how do I explain?
Hmm.
Uh,
It's okay. It's okay. Take your time. Think about it.
what does the gradient mean, right?
Yes. So can I say that this 2 is already being divided by 1? Like, isn't that the same thing?
Yeah,
Right? Okay. Now, do you see that in front of delta y, you have this 2? And what do you have in front of delta x?
1.
Exactly. Now, this is really telling me, all this is telling me is that when my change in x is 1 unit, okay, that means my change in y is 2 units. That's basically it. That's what the gradient means. That when it's also equal to saying that when x increases by 1, when x increases by 1, my y increases by 2. That's basically it. So that means if this is the x-axis, right, on this one, this is the x-axis and this is the y-axis. What the gradient really tells me is that when my x value increases by 1, right, this was my change in x equal to 1. And when my change in x is 1, always, it is always 1, then the change in y in this case is going to be 2. This is what the gradient represents. And for example, now if the gradient is equals to 6 for this line and the gradient is equals to 2 for this line, this is telling me this line m is equals to 2 means that when change in x is equals to 1, okay, then the change in y is going to be 2. Okay. But this line, which is much steeper, what that tells me is that for when my change in x is 1, my change in y is much larger, which is 6. Because if if you see that the gradient is equal to 6, what is gradient? That's a change in y over change in x. And you can always write 6 over 1 as it's the same thing. So the change in x is what? That's 1. And the change in y is what? That's 6. Right? So that basically tells you that when I increase my cause by 1 unit, by how much does the effect increase? Yes, Navia. Have I lost you? Or do you get it? It's
no,
one of the
Deep,
most,
I got it. I
yes, it
got
is
it.
one of the most beautiful concepts in mathematics. And it's very, very important to understand what the gradient represents. If you get the gradient, you'll be able to, you'll be able to figure out most of physics pretty easily. Okay. So that was a basic interpretation of the gradient. And gradient is also equal to rise over run. Rise over run. Have you seen this formula as well? Rise over run.
Yeah, that and y2 minus y1 divided
Why
by
do
x2 minus x1.
exactly? We'll do that formula in just a bit. Now, rise is basically your increase in y, right? Because it's the graph rising. That's the change in y. Do you see that? This is the change in y. This
Yeah,
is the change in y. This is the amount of rise that you get in the graph. And what is the change in x? That is the run, right? How much your person is running to the right. So that's just run. So that's why it's basically the same thing. Increase in y and increase in x. So by the way, can you look at the graph and see which one is having a more gradient without having the numbers? Yes.
the
Isn't that the slope,
the
right? You can
steep
see that
one.
this is exactly. If if the graph, if the gradient is steeper or higher, that means the slope is higher. It's steeper, right? So that means if graph steeper, that means the gradient is higher. Now, what does the higher gradient mean? That means that if x increased by 1, your y increases by more, right? Because if the gradient was not very steep, that must mean that when you increase x, your y did not increase by that much. Now we'll have a look at this example. So we'll have a look at this example. We'll use the same example of screen time and Dant. Now what I want you to do is, I want you to find out the gradient for all three of these, right? You have the points, you have all of the, the labeling, and you have all of the dots. Can we find out the gradient for all three of these kids? What do you think? So let's call this M1. This line has gradient M2 and this line has gradient M3. Can we find out M1? How do you find out M1?
Is it 3?
3. Okay, that's right. And the general way of doing that would be what? You just take change in y with change in x, which is y2 minus y1 over x2 minus x1. Then, you take 2 points, right? Let's just take 2 random points. Let's take this point and let's take this point. Now, how do you find out the change in y? That's just 9 minus 3, right? This is the change in y.
Yeah.
9 minus 3. So 9 minus 3 divided by what is the change in x? That is 1, right? 2 minus 1. So that
Yeah.
means that's just 1. So that means, do you see that the gradient in this case is, no, wait 1 second. No, that was not 1. That was 2. This is the change in x, right? We took this point and we took this point. So the change in x is this value. So that was 2. So that is 2. So the gradient came out to be 6 over 2, which is equals to 3. Now, what does the gradient equal to 3 mean in this case? What do you think? How do we interpret that number by our variables?
Um,
Yes. M1 was change in y over change in x.
yeah.
And if you write change in y over change in x as 3, can we say that 3 is being divided by 1 because that's the same thing?
Yes.
That means, what does this mean? Yes.
That means like y is like it increased by 3.
Yes. It means very specifically, when x increases by 1 unit, by 1, y increases by 3 units, right? Now, for this specific example, what is on the y-axis? Dant. And what is on
Yeah.
the x-axis?
Screen time.
Screen time. Okay. So can I say that for this gradient, the first student, the first child, M1 basically means when it's 3, it means that when 1 hour of screen time is increased, screen time increases, Dant increases by 3 hours. 3 times, sorry. 3 times. Do you get what the gradient means in this context? Yes
Yeah.
or no?
Yes.
Right? So you can literally, like, you can have a look at it. That means if this is my change in y, so change in x, right? I increase my screen time by 1 hour. 1. What is the extra change in x? That is 3. That is 3. Now let's have a look at the other kid. Pick off any point. I increased my screen time by 1 hour, right? So I came from 3 to 4. Now I see that as I increase my screen time by 1 hour, my increase in Dant is also 1. But for the lenient kid, I can see that, let's say I increase my screen time by 1 hour. Let's say this one, right? I increase it by 1 hour. But you see that the extra Dant that I get is only 0.5. So that means I'll basically need to have at least 2 hours of screen time to actually have one Dant. Does that make sense?
2 Dant, right?
No. Let's calculate the gradient. Let's check. The gradient for M3 is what? It's change in y over change in x, right?
Yeah.
Let's pick off any 2 points for the third line. Y2 minus y1 over x2 minus x1. Let's calculate the gradient. This one
Um,
and this one. Yes.
yeah.
Now let's check. what is this change in y? Change in x. Change in x is
6,
equals to 2 and 8, 6. And what is the change in y?
3.
It is 3. No, 3. Okay. So that means that if you were to take the change in y, which is 3, and you take the change in x, which is 6, this comes out to what? This comes out to 1 over 2, which is basically just what? 0.5,
0.5.
right? So if M3 is 0.5, 0.5 is equals to change in y over change in x, right? Can I write it as 1? 0.5 as 1, divide by 1. This change in
Yeah.
y is basically what? This is 1. And what is the change in y? That was 0.5. So how to interpret this? That basically means that this kid, which has pretty lenient parents, that when x increases by 1 unit, okay, that means my y increases by 0.5. Now, instead of writing x and y, I could also write these variables, right? Screen time and time. So that means I could write, instead of x, screen time, and what do I write in front of y? I can write instead of y, dant.
Done.
So that means the number is telling me that when my screen time increases by 1 unit, my dant increases by 0.5 units. Whereas for the strict one, how is that guy different in terms of the gradient?
How
The
what?
first one. The first one, how is he different in terms of the gradient?
Because like when he has 1 hour of screen time, it just increases by 3.
Exactly. And what about the lenient one?
When he gets 1 hour of screen time, he does 0.5 dant.
Exactly. So it's always about the increase. That when you increase your cause by 1 unit, by how much does the effect change, right? That's exactly what we're trying to study. That when I increase my value of x by 1 unit, by how much does the y change? That's exactly what we're trying to study, right? For the strict kid, we see that when the strict kid increases by screen time by 1 unit, the extra done that he gets is a lot more compared to the lenient one, right? This kid can, like, have much more hours of screen time, and he might still not get a lot of dant compared to this guy, right? Makes sense? Like, this kid at 8 hours of screen time is only getting 4 dant, whereas this kid at 2 hours of screen time is getting even more dant, right? Isn't that crazy? Make sense? So do you see how we read gradients?
Yeah.
Really important. Perfect. Okay. Now, by the way, if you were to make a graph between grades and studying, what do you think the graph would look like?
Like
What?
the more
Hmm,
hours you study, the more
hmm,
higher your grades go, so straight line.
you're right. Okay. Do you think it would be a straight line, or do you think it would be slightly curved?
It could be slightly curved, yeah.
Okay. Do you think it would be curved like this or like this? What do you think?
This one?
This one?
Yeah, I
That's
think.
right. That's right. In fact, the relationship between study and grades is not a linear one. It's not an exactly one-to-one relationship that you keep on increasing your study time by 25 hours and your grades will increase by, I don't know, Mars distinction or whatever you want. But it's not a straight line, because what you see is the graph actually looks something like this. Now, this is actually a curve, right? And a curve always has changing gradients. Changing gradients. Now, have a look at this. What is this? What does this graph really tell me? This graph tells me initially when you increase your screen time, not screen time, when you increase your study time, your grades increase by a lot, right? Well, if you're studying nothing and you start studying 1 hour, what do you think? Do you get a big jump in your grades?
No.
No, you don't. No, let's say, you were not studying at all, but then you started studying like 2 hours every day. Don't you think there would be like a huge difference,
Yeah, a slight
right?
one.
No, no. There would be a big difference compared to the case that I'm about to tell you. For example, if you're already studying like 10 hours and then you like increase it from 10 to 11 hours, do you think that would make a huge difference on your grade?
Yeah.
It won't. Because don't you think that it's much easier to get from 30% to 60%? But isn't the journey from 90% to 100% much more difficult? Right?
Very much. Very much.
Exactly. Exactly. It's much easier to go from 30 to 60. Like, even if a kid starts to, like, if the kid, just starts paying attention in school and just starts, showing up to classes, the grade jump for like very little effort might be much greater. But, for the kid that's aiming for the world distinction, from 90% to 100%, it's going to take you extreme amounts of time just for that last 10%. You've got to squeeze this out, right? So that's why the graph actually looks like this. Initially, what happens is, and you could make this graph for example, sports. For example, instead of studying and let's make another graph. Let's make another graph. I've made it curved. I've curved the curve. For example, let's say this is your practice. This is your practice on, I don't know, what sports did you play? What sports did you play?
Badminton.
Badminton? Right. So that, let's say this is your practice hours on badminton. Okay. And let's say that the y-axis is your badminton performance. Do you think it would just keep on increasing by the same amount every day? You will get really good initially, right? But then after that, to get like more improvement, you will have to like play hours and hours and hours and hours. That's exactly how all of the sports work, right? So that means initially what happens is that, for example, if you take the study in grades part, initially when you increase your study hour by one, okay, the grade increase that you get is like very large. You could like go from, let's say you could go from I don't know, let's say 20% to 40. Okay, so that means you increase your grade by 20%. But then what happens is, if you keep increasing your study hour by another hour, right? Then you might increase your grade, but it might be a little bit smaller. Let's say you only increase your grade by 15% now. Then what happens is, you increase another hour of studying, but now you see that the extra increase you're getting is even smaller. Let's say now your grade only increases by 10%, right? Then what happens is, do you see that for the 1 hour increase of study time, now your grade only increases by 5%? That, like, the change in y is getting smaller and smaller. Initially, the change in y was pretty large. But what happens when you're studying, like when you're already studying 8 to 9 hours, and increasing one more hour will not increase your grade by a lot. It might only increase it by 2%, right? And that keeps on going on and on and on and on. And that's the same story for all of the performances. For example, if you're going to the gym to build muscle, initially you feel like, if you go to the gym for 2 months, you just feel like, you're Chris Bum and you're like you're going to win the Olympiad and you're the best bodybuilder in town. But initially your progress will be very fast. But what happens later on is that, as you keep on going to the gym every day, every single day for years and years and years, progress becomes very, 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 very slow. And that's, all kinds of progress looks like this. To master the last part of any kind of performance, you've got to put in exceptional hours. That means if you want to go from 40% to 50%, versus if you want to go from 95% to 100%, this will only take like minor effort. This won't even, like, you could just start, I don't know, you could just start doing something a tiny little bit better and you will get so much better at it. But to get from 95% to 100%, you've got to put in hours and hours and hours. In fact, those hours can be the difference between being Messi and Ronaldo, right? Those guys have put in extreme amounts of time, they've put in extreme amounts of efforts, and they've played so many games. And they're already so good that it takes so much effort to be even better, right? Because they're already at the end of the curve. Does that make sense?
Yes.
Yes. Do you agree? Do you agree now that, it's much difficult to improve down the road?
Yes.
So that's why progress at the start is very easy, very, very easy. It becomes much more difficult later on. And that's why, in fact, initially, initially, you get the most amount of progress with the least amount of effort, right? But as you become better and better and better, you get very, 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 very little improvement for a lot of uh, effort put in. That's the story with all kinds of pursuits. It could be studying, exercising, cooking, uh, I don't know, any kind of activity, any kind of what I don't know, name anything. What do you think?
Um, uh, Stitching? I don't know.
Stitching, okay. Anything could be. The driving, for example, right? If you want to race, right? In racing, if you put in like 3 to 4 hours, okay, you might get from 0 to 50. But to get from 50 to 60, that's more difficult. Then from 70 to 80, even more difficult. 80 to 90, it could take you like years. Then 90 to 100, it could take you decades. So that's what I'm basically trying to tell you over here, that in a curve you have changing gradients. Changing gradients means that the relationship between cause and effect keeps changing. You see that over here, that for 1 unit increase in x, my change in y was higher. Then for 1 unit increase in x, my change in y became smaller. Then I keep seeing that over the course of this journey for studying, that when I when x keeps increasing by 1 unit, the extra the extra change in y, the extra change in y starts to fall, right? The extra one. If y is still increasing, you are still getting progress, but the progress has slowed down a lot. Okay. Now, how do you calculate the gradient of a curve, by the way? You can't really do y2 minus y1 over x2 minus x1 for a curve. Did you know that? How do I find out the gradient
Yeah.
for this curve? Any idea?
Um,
So let's say I want to calculate the gradient for a curve. How do I calculate the gradient for a curve? I can't exactly do x1 over x2 and then y1 over y2. I can't do that. Y2 minus y1 over x2, x1. I can do that. Why? Because
Rise
that
over,
would be that would be for this line, right? How am I calculating it for the curve then?
rise over run.
We can't do that either. For the graph, we can do y2 minus y1 over x1 minus x1 or rise over run. For a gradient of a curve, what you do is you take tangents. That means what you're going to do is, if you want to calculate the gradient at this point, you draw a curve that is tangent, okay, just to tangent to that point. It's barely touching that curve. And then you take this straight line, okay, you take the straight line and you calculate the gradient of this straight line. So that means you take this as y2 x1, y2 x2, and you take this as y1 x1, and then you find out the gradient of this line. Okay, then you find out the gradient of this line, which is y2 minus y1 over x2 minus x1. So that's how you find out the gradient of the curve. You'll have to do, if you want to find out the gradient at a different point, then you'll have to take a different point and you calculate the gradient for that point. Then if you want to calculate the gradient at this point, you'll have to calculate the gradient at this point, right? Make sense? We'll do this in more detail later on, but I think that's it for now. Yes, questions. Bring in the questions. What's up?
Um, what's a tangent?
Hmm. A tangent is basically, I believe you haven't studied this in your school yet.
No.
Okay, okay, that's fine. Although this is, uh, if I were to go into more technical details, this is a part of mathematics. This is a real big chapter of mathematics. I'll tell you the overview just for now. I'll tell you the overview just for now. That if you want to calculate the gradient of a curve, it's pretty easy to do it for a straight line. You just do change in y by change in x. But if you've got a curve like this, okay, this is y, this is x. Do you see that the gradient at every point is changing? If you had a straight line, the straight line had a constant gradient, right? If you keep increasing 1x, your y increases by same amount. If you keep increasing 1x, your y increases by same amount. If you keep increasing x by one amount, then your y increases at the same rate. So a straight line, a straight line actually has a constant gradient. What does a constant gradient mean? That means your rate of change of y is same. That means that by how much y changes when x increases is the same. Is the same. Let's take the example of the falling ball. I think we did that. Uh, for example, in this case, you had constant acceleration of the ball. The ball was falling down, okay, and it had a constant acceleration, which means that every 1 second the ball's velocity increased by 9.81. And the ball's velocity kept on increasing by the same value, 9.81, 9.81, 9.81, 9.81. This is what we mean by constant acceleration, right? The change in velocity was the same throughout every point. But for the curve, that's not exactly the case. In the curve, what's happening is that the change in y and the change in x relationship is changing throughout the entire journey. It's a slightly complex topic. It's taught in much more detail in mathematics. And in fact, send you a very good video that covers all of these concepts for mathematics. Why? Because these concepts are really, really important for physics. If you want to study physics, what we'll be doing, in just a few days is we'll be studying distance time graphs. We'll be studying velocity time graphs. And in order to understand those graphs, we'll be able to first understand how graphs work. And if we don't know how graphs work, then we won't be able to interpret those speed, distance, time graphs. And that's the entire reason why graphs seem very confusing. If you don't understand the language of graphs, then you won't be able to understand what the story they're telling you. Okay, so what I was saying is, for the curve you have a changing gradient. You have a changing gradient. That means the slope is changing, right? And you can look at it. Do you see that for the straight line, the slope is the same? The steepness is the same for the entire journey, right? Imagine there's a car. Do you see that the angle of steepness is the same for the entire journey?
Yeah.
Right? But what happens for the curve? Do you see that the slope is changing? Let's calculate the slope like this. For example, let's take this point. Isn't this the slope for the starting, right? Initially, the slope is steep. But what happens after a few seconds, let's say a few amount of point of x's? Do you see that the slope is decreasing, right? The slope is
Yeah.
decreasing. The slope is decreasing. The slopes keep on falling, right? So do you see that in this case, the slopes for curve are falling? Why? Because literally you can see the steepness is decreasing. The steepness is falling for the entire journey. That's literally what we're saying. The gradient is changing. The slope is changing. And how do we find out the slope of a curve? Like, how do I find out the slope at this point? How do I find out the slope at this point? Because the slope is changing every second. Slope change, slope change, slope change, slope change. It's kind of like the steepness is changing. It's like a hill, right? The hill has a varying steepness. But if you have like a very straight road, the steepness is the same. But for the curve, the steepness keeps on changing. Now, how to find out the steepness of a curve? I will send a YouTube video for that, because that's a topic of mathematics. I've tried to cover a lot of mathematics of gradients and y is equals to mx plus c and x and y, but I'll send you a really, really good video with animations for the curve of a slope. Okay.
Okay.
Okay. Any questions so far? Up till this
Mm,
point? No, all good?
No, only that.
Okay, that's fine. Don't worry. The slow part, it is a new concept. I'm sure it's a little bit difficult to grasp, but I'll send you a video for that. There's, the brilliant videos on YouTube about that. I'll send one. Do watch it. Try to understand it, and you can let me know when you have questions when we see you in the next class. Okay. I
Okay.
think then that'll be all for today. We can't really start the next thing before we get to this part. Okay.
Okay.
Okay, perfect. I have updated the link and I'll send you the video in just a bit. Do watch it and do understand it. Do write it down as well. And then, we'll start the speed, distance, time graphs in by Monday, hopefully. Okay.
Okay.
Okay, perfect. Great. I've recorded it. Make sure, Amna watches the recording. When will she be back?
She'll be back